Okay, let's look at some theories of intraseasonal oscillations, intraseasonal variability, which of course is going to focus on MJOs and mesos. And I will start, this is basically Bin Wang's chapter in the Lau and Walliser book that we have been following. And start with a figure from Bin Wang's paper that recently came out. So this is a schematic diagram illustrating three-dimensional structure of the MJO mode. BLMC represents boundary layer moisture convergence. So this is good to keep in mind in terms of what the observations indicate and how theories, multiple theories, have been trying to explain the structure, the propagation, and the processes. And in general, I like to remind people that when you have multiple theories, that means the understanding is incomplete and the data can be fit with multiple theories, and more data is needed to weed out the theories or build better hypotheses and lead to a more unified theory and so on. Nonetheless, let's say we have here, let me do the laser pointer again. So we have the convection, which is the key ingredient of interseasonal oscillations, of course, and you have the vertical motion, and you can see there are tilted structures, which we will get into later on. So you have low-level convergence and upper-level divergence, so you have subsidence on either side. In the lower atmosphere, you have a wave-like structure extending forward that's reminiscent of a Kelvin wave, and behind you have a Rossby wave structure. So the first ingredients are these waves, and the key struggle with theories has been to explain the speed of propagation, which is not as fast as a free Kelvin wave. It's much slower, and then the ideas have evolved that this is a coupled convectively coupled Kelvin wave, convectively coupled equatorial waves, and not free waves. That's why they move slowly. The other ingredients that are always involved are the moisture convergence. To feed the convection, obviously you need moisture convergence. The rising air and the precipitation and the divergence end up with the structure above, which is the opposite of what you see at the surface, and there is the boundary layer, and the debates have been about whether the moisture convergence in the boundary layer and the frictional convergence that is important, and or the free tropospheric moisture convergence that is important, and how to drive the instabilities and the eastward motion, for example, and how the anomalies of winds associated with the convective phase propagating eastward with the easterly anomalies on the eastern side and westerly anomalies on the western side can potentially feed back to the MJO and also facilitate the eastward propagation. So we'll see some theories which invoke these wind anomalies on top of the background winds, the seasonal winds, let's say, and how those affect the fluxes. So the other thing that's always important is the surface fluxes, latent and sensible heat fluxes, and you have cloud top temperatures, either shortwave reflection and outgoing long wave, so you have radiative cooling. So when you have heating from below and cooling from the top, you obviously create instabilities, and the question is, how do they project onto these structures, how do the scale selections happen, and so on and so forth. So the same paper by Bin Wang provides this schematic diagram illustrating the essential large-scale dynamics of the MJO. Because MJO has had so much observations, data, field campaigns, theories, and so on, we'll start with this and will tack on the mesos at the appropriate time. So you have SST ingredient that is important, and we will see in a minute why. The basic state moist static energy, that's always critical. So when you have moisture convergence and moist static energy and instability build up, that's always good for moisture feedback to diabatic heating. And you have various dynamics that are also building on the moist static energy. So you have the low frequency waves and the boundary layer frictional moisture convergence, which is the one of the theories that we will see in a minute. So there are feedbacks between the diabatic heating and these dynamics of waves and frictional boundary layer convergence, moisture convergence, and of course dynamics also affects the moisture feedback, the dynamic heating. So you have a system that also often is called multi-scale system, because convection in general is embedded in the large scale circulation as well. So this kind of divergence and subsidence, these are larger scale than the convection itself, which is typically a small scale process, and the C-source temperature anomalies associated with the MJOs or the mesos tend to be much smaller scale in space than the atmospheric circulation and convection. From the book, this is from the Binmang paper again. The following set of statistical features is proposed as defining the horizontal scale, spatial structure, propagation, including the direction and phase speed, and annual variation of the interseasonal oscillation. Planetary scale circulation coupled with the large-scale convective complex, which is what makes it a multi-scale system. Horizontal circulation comprising equatorial Kelvin and Rossby waves, and baroclinic circulation with boundary layer convergence preceding the major convection region. So we can see there is convergence ahead of the convection. All these little things matter to explain the eastward propagation. So we discussed that a little bit when we talked about the mesos. Note the references given in there. You can follow those up. Slow eastward propagation, about 5 meters per second. Sorry, the negative sign I'm missing there. In the eastern hemisphere, and longitudinal dependence of amplification. So coming from the western Indian Ocean into the western Pacific, you have the slow eastward propagation, prominent northward propagation, and off-equatorial westward propagation during boreal summer in the summer monsoon region, which is our mesos. More stringent validation characteristics include the multi-scale structure of the convective complex and the role of multi-scale interactions in MJO dynamics. Even though multi-scale sounds like it's a very generic term, it has a lot of meaning because there are supercloud clusters and the large convective structure that's moving eastward, within which you have shorter timescale, 2-day timescale, westward propagating features embedded in them, and so on. People like Andy Maeda have worked a lot on the multi-scale structures and theories based on multi-scale structures. The multi-scale structure of the convective complex and the role of multi-scale interaction in MJO dynamics is thus very important. And finally, the associated interaction with SST variability. So it was noted by T. N. Krishnamurti very early on that the surface heat fluxes associated with SST variability seem to be a key feature of driving the processes that are involved in the eastward propagation of the MJO. The essential characteristics of the MJO system may embrace the following aspect, again repeating some of the points. MJO is a planetary scale dominant zonal wave number 1 and 2. So wave number 1 means it's basically got a planetary scale. Wave number 2 means it has one node in the middle. So the planetary scale circulation system coupled with a large scale zonal wave number 3 to 5 convective complex implying a preferred scale selection that goes on during MJOs. Sorry for the spacing of these things. MJO moves eastward slowly with a speed of about 5 meters per second, which we already said, over the Indo-Pacific warm pool, and 15 meters per second over the Western Hemisphere, leading to the 30 to 60-day oscillation. So once we get past the warm pool where convection is very strong, as the system transitions to colder temperatures over the Eastern Pacific into the Atlantic sector, it's not strongly coupled anymore, so the features are propagating much faster, almost 3 times faster. There's no convection associated with those over colder temperatures. The MJO circulation exhibits a coupled Kelvin and Rossby wave structure. We say coupled because they are moving slower than the free waves. MJO exhibits a gravest baroclinic circulation structure with a backward tilted vertical motion and moisture. This backward tilted vertical motion and moisture are related to the cloud structure, which end up creating these kind of backward tilted structures. So you can see here there is the deep convective cloud here and the shallow cumulus cloud in front of it, which is related to the boundary layer moisture convergence there. So cloud radiative feedbacks are invoked as very important processes in some of the theories, which we will briefly look at in a minute. The MJO system amplifies over the Indo-Pacific warm pool and decays over the cold tunnel in the Central and Eastern Pacific, as I already mentioned, implying that an instability mechanism exists which triggers these waves. So waves are generally a response to some sort of an instability that generates the wave response. Okay. Just briefly, the overview of the theories that are typically involved in MJOs and MESOs include things like wave CISC. You probably know what CISC is. If not, don't worry. It's the convective instability of the second kind. Convective instability of the first kind is where you have warmer SSTs driving rising air and moisture going with it. Convective instability of the second kind involves dynamic feedback, so the rising air and expansion and convection drives surface level moisture convergence, and you have circulation features. And wave CISC is basically the generation of waves associated with the diabatic heating that typically goes with the convective instability of the second kind. This is obviously proposed because it fit some of the data, but obviously doesn't explain all the things that we want explained, so that remains part of the story. Wind evaporation feedback, or WISHI, wind-induced surface heat exchange, basically uses the fact that there are easterly anomalies ahead of the convection, westerly anomalies behind, and it relies on the fact that over the Pacific, the background winds are easterly, the trade winds, so the easterly anomalies associated with the ISOs enhance the wind speed and pick up latent heat flux from the ocean, whereas behind it they tend to slow down the background winds and reduce the wind speed, increase the latent heat flux, and reorganize the convection following the convective phase. Of course, the problem immediately you can see is that the background winds over the Indian and West Pacific Ocean are in fact easterly, they're westerly and not easterly. So this idea already runs into trouble, but there are other aspects that are used to try to explain them as well. And many of these actually depend on the convective parameterization used. When you take the simulation of ISOs from general circulation models or coupled circulation models or forced atmospheric models, and you diagnose these kind of processes, often the convective parameterization that's used in the models tends to influence the conclusions you come to in terms of wave CISC or WISHI or frictional convergence instability and so on. So frictional convergence instability basically requires surface level processes, kind of what we talked about before in terms of the vertical shears, horizontal vorticity, related vertical motions, and surface convergence, cyclonic motion driving moisture supply and instabilities. Does it work? Well, not always as well. So cloud radiation feedback's a very broad term, but generally the shortwave reflection, long-wave cooling, and the impact together with the surface fluxes in terms of the moisture feedback and generating instabilities is captured in these models called cloud radiation feedbacks, especially in the meso region. The northward propagation which happens in boreal summer, it's not always clear whether those are generated in the northwest tropical Pacific and propagating into the Indian region as Rossby waves, and if so, how the timescales are selected, or whether they are just generated in the Indian Ocean, let's say in the western Indian Ocean, propagating eastward but then being steered northward, and if so, there is something proposed as convection thermal relaxation feedback, where convection, for example, reduces the instability in the atmosphere or increases the stability, and then you have radiative and thermal cooling processes which re-establish the instabilities, and that can explain the northward propagation. Convection water vapor feedback and the moisture mode again involve the fact that convection moisture, the nonlinear Clausius-Clapeyron relations can drive instabilities and can explain the eastward propagation and the coupled Kelvin waves and Rossby waves and so on. Multi-scale interaction theory, a very broad term, but tries to look at the large-scale convective circulation, large-scale circulation associated with the convection, and the smaller scale higher frequency processes involved embedded in the large-scale circulation. We will look at what we mean by that as a figure in the next podcast. Mechanisms of boreal summer interseasonal oscillation. We talked about the vertical shear versus the horizontal shear. So the vertical shear basically gives us the horizontal vorticity, vertical motion, frictional convergence, and there is a background moisture gradient towards the north because of the monsoonal background circulation, which generates moisture feedback ahead of the convection and generates a northward propagation of the convection. But there are now ideas being proposed that it's actually the meridional shear of the zonal winds, which is also strong during the monsoon, and that's what gives a coupled SST zonal wind gradient mode, which can explain the energy for the propagation in terms of barotropic instability instead of the baroclinic instability, and so on. Rather fast, but we will come back to each of these points later on. Atmosphere-ocean interactions, we already mentioned SSTs and surface fluxes. There are many model experiments done, and typically coupling helps with the phasing of SST and convection. When you force the atmospheric model with SSTs, the convection and SST tend to be in phase, whereas if you couple it, then SST leads by up to 10 days, convection follows, SST cools, and then SST reorganizes, and so on. And also coupling, ocean-atmosphere coupling tends to improve the propagation speed, MJO variability or amplitudes, structures, and so on. So there is at least indirect evidence that coupling is very critical for interseasonal oscillations. Okay? So that's a quick run through the overview, but we will slowly build on the details of the theories with mathematical equations as we go along. All right? Hopefully this orients you properly for what's coming next.